Hey there, and welcome back to the Deep Dive. Today, we're really diving in, taking a plunge into, well, one of the most exciting and honestly pretty mind-bending frontiers in tech right now. It's the place where quantum computing meets artificial intelligence. We're calling it the quantum leap for AI. And this deep dive, it's especially for you. We've built it directly from this stack of articles and research you shared with us. Our mission really is to cut through some of the hype, and the complexity. We want to pull out the most important, maybe the most actionable insights from these sources about this really cutting-edge field.
Exactly. Think of us as your guides for this one. We want to help you understand the fundamental building blocks of quantum computing first. Then how it's starting to interact with AI, the specific problems researchers are hoping to tackle, where things actually stand, right now in June 2025, and also the pretty significant challenges that still need solving. It's really about getting to the so what of this whole quantum AI fusion idea.
Okay, let's unpack this then. Before we even jump into combining these two titans, we really have to get a handle on what makes quantum computing so fundamentally different from the classical computers we're all using every day, maybe even right now to listen. What's the core distinction there?
Right. The core distinction, it really boils down to the absolute basic unit of information. So classical computers, they use bits, simple switches, right? Either on, that's a 1, or off, a 0. Pretty straightforward. Quantum computers, though, they use qubits, quantum bits. Now, a qubit, it's different because it can be in a state of superposition.
Superposition. Okay, that sounds complex. It's like being in two places at once, kind of.
Well, yeah, kind of. It means a qubit isn't just stuck being 0 or 1. It can be 0, it can be 1, or, and this is the crucial part, it can be a combination of both at the very same time. It's represented as probabilities. Think of it like a spinning coin just before it lands, right? It's sort of both heads and tails simultaneously with a certain chance for each. And this ability to hold combinations is why even a few qubits can potentially store and process, exponentially more information than the same number of classical bits.
Wow. Okay, so it's not just black and white, 0 or 1. It's a whole spectrum of possibilities in between.
Precisely, a spectrum based on probability. And then you add entanglement into the mix. This is maybe the weirdest, the most counterintuitive quantum thing. When qubits are entangled, they get linked up. Their fates are correlated no matter how far apart they are physically. If you measure the state of one entangled qubit, you instantly know something about the state of the other one, even if it's, light years away.
Okay, hold on. That sounds like something straight out of science fiction. What's the actual practical point of this weird link?
It sounds weird, yeah, but it's not just weird. It's a fundamental resource. It's key for quantum computation, this spooky action at a distance. I think Einstein called it that, right? It gets leveraged by quantum algorithms.
Right.
They use it to perform computations in ways that, classical computers just physically can't. And because of superposition, you also get something we call quantum parallelism. So instead of crunching numbers one after another sequentially, like a classical computer, a quantum computer can effectively explore and compute across a huge number of potential outcomes all at once, simultaneously. Now, this isn't like a magic speed up for everything, but for certain specific kinds of problems, it offers this potential for exponential speed ups, huge gains.
Right, so you've got these incredible powers, superposition, entanglement, this parallelism, but you need special instructions to use them, don't you? That's where the quantum algorithms come in.
Exactly right. You can't just run standard code. You need specialized tools, algorithms designed specifically to harness these quantum effects. The sources you sent over mention some famous examples like Shor's algorithm. If you've heard anything about quantum computing being a threat to current cybersecurity, it's probably because of Shor's. It can factor large numbers really, really efficiently. And that specific task, it's the foundation of most modern public key cryptography. So yeah, big deal. And then there's Grover's algorithm. That one offers a potential speed up for searching through unsorted databases. But again, these aren't things you'd run on your laptop. They're built purely for quantum hardware.
Okay, that paints a picture of immense theoretical power, groundbreaking algorithms. But, theory is one thing, reality is often another. Where are we actually right now with the hardware, specifically here in June 2025? The sources keep bringing up this term, the GNXQ era. What does that practically mean for quantum computing, right this second?
Yeah, NISQ. As of June 2025, we are definitely firmly in the noisy intermediate scale quantum era. NISQ. Okay, so intermediate scale, that part means current quantum processors are still relatively small. We're seeing systems with, say, tens to maybe a few hundred qubits, although in labs they're pushing towards the low thousands experimentally. Still smallish, relatively speaking, but the really critical word there is noisy.
Noisy.
Yes, these qubits, they're incredibly fragile, extremely sensitive. They lose their delicate quantum state. That property is called decoherence, just from tiny environmental disturbances, like tiny temperature fluctuations or stray electromagnetic fields.
So it's like trying to whisper a secret in a really, really loud room. Is that a fair analogy?
It's a bit like that, yeah. Or maybe like trying to balance a super sharp pencil perfectly on its tip, the tiniest vibration, the slightest tremor, and poof, it falls over. This noise, it introduces errors into the computation, lots of errors. And building quantum computers that can actually detect these errors and correct them effectively, that's called fault tolerance. Achieving that is it's a monumental engineering challenge. It's still very much a work in progress. So yes, the potential is real, absolutely, but the hardware right now, it's limited in size and it's prone to errors.
Okay, that makes a lot of sense. So quantum computing has this unique, potential-rich, but right now noisy and error-prone power. On the other flip side, classical AI, it's achieved incredible things just in the last few years. Computer vision, NLP, generative models like we're seeing everywhere. So why the push to combine them? What are the limits of classical AI that this quantum leap might actually help us overcome?
That's a really key question. Classical AI is amazing, truly amazing, at pattern recognition in large data sets, making predictions, tasks that fit traditional computing models well. But it hits fundamental roadblocks. It hits walls with certain kinds of problems, specifically problems that scale exponentially. One huge bottleneck is dealing with genuinely massive search spaces. Think about really complex optimization problems, finding the absolute best route for, thousands of delivery trucks simultaneously, or designing the most efficient financial portfolio with countless interacting variables, or exploring the vast, vast landscape of possible molecular structures when you're looking for a new drug. The number of possibilities can just explode, becoming larger than the number of atoms in the universe. It just completely overwhelms classical computing power very quickly. Another major limitation, and this one's directly relevant to science, is accurately simulating quantum systems themselves. Trying to model the precise behavior of molecules, how electrons interact, how chemical bonds form and break. Classical computers really, really struggle with this. The computational complexity just grows exponentially with the size of the molecule. So doing accurate simulations for anything beyond maybe a few dozen atoms becomes incredibly difficult, or often just impossible. And that's a huge drag on progress in drug discovery and materials science. And finally, while classical computers are great at linear algebra, which is core to a lot of AI, certain types of linear algebra operations on truly colossal datasets can still become computationally too expensive, just too slow. So the why we need to combine them, it's because quantum computing offers a fundamentally different way of processing information. It offers a path that could bypass these specific exponential bottlenecks for certain specific AI problems. It's not about making your current photo recognition AI faster at everything. It's about tackling problems that are currently just intractable, unsolvable.
Yeah. Okay, now this is where it gets really interesting for me. How are researchers actually starting to, stitch these two incredibly powerful fields together? What are the key areas of synergy that the sources you looked at are highlighting?
Right. The most talked about area of integration, the one getting a lot of attention, is quantum machine learning, QML. And the basic idea here is using quantum computing, or sometimes just quantum principles, to enhance or maybe accelerate various machine learning tasks that classical AI already does. A big focus within QML is on quantum enhanced optimization. Like we just discussed, many, many machine learning tasks boil down to optimization problems, right? Think about finding the optimal weights and biases in a deep neural network during training, or finding the best set of features to feed into a model. Quantum algorithms like QAOA, the quantum proximate optimization algorithm, or different approaches based on quantum annealing, which companies like Canada's D-Wave are famous for. These are being explored pretty intensely. The hope is to see if they can find better solutions to these optimization challenges, or perhaps find good solutions faster than classical methods. Then there's the idea of leveraging quantum algorithms specifically for data analysis and linear algebra tasks within AI. Since so many classical ML algorithms rely heavily on linear algebra, solving systems of equations, matrix manipulations, eigenvalue problems. Dot quantum algorithms like the HHL algorithm, they offer theoretical speedups for these specific mathematical operations. However, there's a major practical catch here. It's that data input-output bottleneck, the I/O problem.
Ah, right, getting the data in.
Exactly. Getting massive amounts of classical data into a quantum state that the algorithm can actually work with efficiently, that's a huge hurdle. It can often completely erase the theoretical speedup you were hoping for from the quantum algorithm itself. It's like having a super fast engine, but only a tiny fuel line.
So the quantum math might be fast, but feeding it the problem is slow.
Often, yes, especially for data-heavy AI tasks. It's a really significant challenge people are working on. Researchers are also starting to build entirely new types of AI models, things called quantum neural networks, or QNNs. Now, these are still highly experimental architectures. They use quantum circuits as their fundamental building blocks. They're trying to leverage things like superposition and entanglement within the network itself during the learning process. The hope, or maybe the question, is whether they offer fundamentally different learning capabilities, maybe better expressiveness, or perhaps they generalize better for certain types of complex data compared to standard classical neural networks. It's a very active research area, really exploring if quantum mechanics offers a genuinely new way to do learning. And one more area to mention is potential in quantum generative models. Generative AI models, GANs, VAEs, diffusion models. They try to learn the underlying structure or distribution of data so they can create new examples, like generating realistic images or text or music. This often involves a tricky step called sampling from very complex, high-dimensional probability distributions. And there's a thought that quantum computers, due to their nature, might be inherently better suited to performing this kind of complex sampling. This could potentially lead to more powerful generative models, maybe creating more realistic or diverse outputs. Still early days, but promising.
Okay, shifting gears slightly, the sources also really highlight a profound and honestly quite concerning impact, the one on our current security landscape, cryptography. How exactly does quantum computing threaten the digital security we rely on every day? And what are the solutions being developed for this coming quantum era?
Yeah, this is absolutely critical, and it's something governments and major organizations worldwide are taking very, very seriously. The primary threat, as we touched on earlier, comes directly from Shor's algorithm. See, security of most of the public key cryptography we use globally today, the stuff that secures your online banking transactions, secure websites, that little padlock, HTTPS, digital signatures, secure email, all of that. It relies on the mathematical difficulty, specifically for classical computers, of factoring extremely large numbers, or solving related problems like the discrete logarithm problem. These are just too hard for current computers to crack in any reasonable time frame. Shor's algorithm, however, provides a method, a recipe for a sufficiently powerful, and this is key, fault-tolerant quantum computer to solve these exact problems efficiently, like way faster. So if, or maybe when such a machine is built, it could basically break the encryption that protects a vast, vast amount of sensitive data worldwide. Stored data, future communications, everything. Yeah. This is why there's this intense global race, not just to build the quantum computers themselves, but also to develop and deploy new ways to secure our data against these future quantum attacks. It's a race against time, in a way. Fortunately, solutions are being actively developed on two main fronts. The first one is post-quantum cryptography, or PQC. Now, these are completely new classical algorithms. They run on regular computers, but they're designed using different, more complex mathematical problems, things like lattice-based crypto, code-based, hash-based, that are believed to be hard to solve for both classical and quantum computers. There's a huge global effort underway, led by organizations like the U.S. National Institute of Standards and Technology, NIST, to standardize these new PQC algorithms. And organizations everywhere, including many here in Canada, are already starting to plan the very complex, multi-year transition away from our current vulnerable encryption methods to these new PQC standards. And interestingly, the sources even mention that AI itself might be used to help vet these new PQC candidates, like analyzing their potential strengths and weaknesses.
Okay, so new classical math problems to resist quantum attacks. What's the other approach?
The second approach is called quantum key distribution, or QKD. Now, this is quite different from PQC. QKD doesn't replace the encryption algorithms themselves. Instead, it provides a way to securely exchange the secret keys needed for symmetric encryption, but it uses the laws of quantum physics principles, like the uncertainty principle, to guarantee security. Essentially, if anyone tries to eavesdrop on the key exchange while it's happening over a quantum channel, like fiber optic, the very act of measuring the quantum state disturbs it. This disturbance alerts the legitimate sender and receiver that someone's listening, so they can discard the key and try again. Its security is based on fundamental physics, not just assumed mathematical hardness like RSA or ECC, but QKD is typically focused on securing the communication channel for key exchange, often point-to-point links, rather than encrypting stored data or replacing public key infrastructure entirely. So PQC and QKD are seen as complementary solutions.
Right, okay. Fascinating stuff on the security side. Let's shift gears again, though, to an area that feels incredibly exciting and maybe more near-term in terms of impact. Molecular modeling, material science, drug discovery. How can this fusion of quantum and AI really revolutionize these fields?
Yeah, this is often highlighted as one of the most promising, perhaps even one of the first really impactful application areas for quantum computers. And it's because it directly tackles that fundamental classical limitation we talked about earlier.
How?
The sheer inability of classical computers to accurately simulate quantum systems, like molecules, beyond a certain small size. Classical machines just hit that exponential wall when trying to model the incredibly complex interactions of electrons in atoms and molecules. And this inability to accurately simulate the world at the nanoscale, it's a massive bottleneck in designing new drugs, discovering advanced materials with specific properties, understanding catalysts, and predicting chemical reactions. We're kind of stuck guessing or using approximations. Quantum computers, however, well, they are quantum systems themselves, so they are naturally suited, in principle, to simulating other quantum systems. They hold the potential to model molecular structures, predict their electronic properties, simulate chemical reactions, and understand complex material phases with far greater accuracy and efficiency than any classical method could ever achieve.
Okay, so the quantum computer's really good at doing the heavy lifting, the simulation part itself. Where does the AI fit into this picture? How they work together here?
Great question. This is where the concept of AI-guided quantum discovery really comes into play, and it gets powerful. It's almost always a hybrid approach. Classical AI isn't replaced at all. It works hand in hand with the quantum simulation. For instance, you can use classical AI upfront for candidate selection. Imagine screening vast classical databases containing millions or billions of known molecules or material structures. AI can rapidly sift through those to identify the most promising candidates, the ones that are actually worth dedicating the precious, computationally expensive time on a quantum computer to simulate in detail. Sort of a smart filter. Then, the quantum simulation runs on the chosen candidates. The output from that simulation, it can be incredibly complex, tons of quantum data. So AI becomes crucial again for interpreting that complex quantum data, finding subtle patterns, extracting meaningful insights, learning those structure-property relationships that might be completely hidden from human analysis. And AI techniques can even be turned back onto the quantum simulation itself, using machine learning to optimize the quantum algorithms being used, making the simulations run more efficiently or more reliably on the noisy hardware we currently have.
Wow, okay. So AI helps choose what to simulate, helps understand the results, and even helps tune the quantum simulation itself. That's a tight loop.
Exactly. It's a synergistic loop. And the potential applications are just huge. In drug discovery, think about accurately modeling exactly how a potential drug molecule interacts with a specific protein target in the body, predicting binding affinities with high precision, understanding complex enzymatic reactions. This could build on amazing AI successes we've already seen, like DeepMind's AlphaFold, predicting protein structures, but add a critical layer of quantum precision to understand function and interaction. It could dramatically accelerate the design of completely novel therapeutics. And in material science, it's about designing new materials, literally atom by atom, to have precisely the properties we need. Think about discovering more efficient catalysts. We desperately need better catalysts for things like producing green hydrogen cleanly or capturing CO2 directly from the atmosphere, both absolutely critical for tackling climate change. Or designing novel battery materials for better EVs and grid storage, new types of semiconductors for faster electronics, maybe even finding materials that become superconducting at much higher, more practical temperatures. The sources specifically mention Canada's strengths in materials research and clean energy, highlighting how these national priorities could be significantly boosted by quantum AI advancements. And it doesn't stop there. It extends to agriculture, designing better, more targeted fertilizers or pesticides, and to industrial chemistry, finding more efficient catalysts for manufacturing processes, reducing waste and energy use.
Okay, the promise there, especially for science and medicine, is just staggering. So that's the potential. But let's ground ourselves again. Where do things actually stand right now, today, in June 2025? Are these kinds of revolutionary breakthroughs happening at scale yet?
Right, grounding is good. As we established, we're still largely operating within that nice, Q, noisy, intermediate scale quantum era. So while there's undeniably rapid progress, lots of exciting experiments, most of the current breakthroughs you might read about are more like proofs of concept or demonstrations on relatively small, error-prone devices. The dream of large-scale, fault-tolerant quantum computation, the kind needed for things like breaking RSA encryption or simulating very large molecules perfectly, that's still firmly in the development phase, not deployed yet. The focus today in the research community and industry is really on achieving what's called quantum advantage. And it's worth maybe clarifying this term. It's distinct from quantum supremacy, which you might remember Google claimed a few years back. Supremacy just meant doing any task, even a contrived one, faster than a classical computer could. Quantum advantage is more practical. It means demonstrating that a quantum computer can solve a useful, real-world problem measurably faster, or maybe better, or perhaps cheaper, than the very best classical methods available today. We're starting to see claims emerge for quantum advantage in some niche areas, often related to specific types of optimization or simulation tasks relevant to chemistry or materials, but widespread, transformative advantage across many industries. That's still something we're actively working towards, and it really depends on getting better, more robust hardware. However, the ecosystem around quantum computing is developing incredibly quickly. That's a really positive sign. There's a growing suite of quantum programming languages, things like IBM's Qiskit, Google's Cirq, Microsoft's QSHAG Plus software development kits, SDKs, simulators that run on classical computers, and crucially, cloud platforms that give researchers and developers access to actual quantum hardware from various providers. Companies like IBM, Google, Microsoft, Amazon, IonQ, Rigetti, and others offer this. And the sources also rightly point out key Canadian players making waves, like Xanadu in Toronto, who are building quantum computers using photonics, light particles, and D-Wave out in BC, who pioneered and specialized in those quantum annealing systems for optimization. All this infrastructure makes quantum resources much more accessible than they were even just a few years ago. People can start experimenting. And underpinning all this activity is really significant global investment. Governments around the world, plus major tech companies and venture capitalists, are pouring billions into quantum R&D. Canada, for example, has its National Quantum Strategy, which is specifically aimed at fostering leadership in the field, developing the needed talent, and accelerating the path to commercialization. It's truly an international race, but also requires a lot of collaboration, which is happening too.
It definitely sounds like incredibly exciting progress on many fronts, the software, the cloud access, the investment. But clearly, as you said, there are still immense challenges to overcome. What would you say are the biggest hurdles, the main roadblocks standing between us today in realizing this full vision of quantum AI impacting the world?
Yeah, the obstacles are absolutely formidable, and the sources we looked at are pretty clear and consistent about them. The single biggest one, the challenge that really underpins many of the others, is still the quantum hardware limitations. Just building large-scale, stable, reliable, and crucially fault-tolerant quantum computers, it remains the #1 engineering grand challenge. Current NISQ devices are simply too small in terms of qubit count and too noisy, their quantum states decohere too quickly to run the most powerful, game-changing quantum algorithms reliably. And this hardware limitation links directly to the challenge of quantum algorithm development. While many promising quantum algorithms exist in theory, like Shor's or algorithms for simulation, implementing them practically often requires that fault tolerance we just mentioned, which just isn't widely available yet at scale. And as we discussed quite a bit, that data input-output I/O bottleneck, just efficiently getting classical data into the quantum computer and getting the results out remains a major practical hurdle, especially for applying quantum speedups to the large-scale classical datasets often used in AI. Then there's quantum error correction, QEC. This is a huge field in itself, developing robust error correction codes, basically. Clever ways to encode quantum information across multiple physical qubits so you can detect and fix errors without destroying the quantum state and then actually implementing these complex codes on real noisy hardware. It's an incredibly complex engineering feat, but it's absolutely necessary if we want to build machines that can perform long, complex computations without errors completely overwhelming the result. Reliability is key.
Okay, so hardware algorithms, data I/O, error correction. What else?
Beyond the technical hardware and software challenges, there's a very real talent gap. There's a significant global shortage of people who possess deep expertise in both quantum physics or quantum computing and artificial intelligence. You need people who can truly bridge these two complex fields to innovate effectively at their intersection. Building up that interdisciplinary talent pipeline is absolutely crucial for future progress. Benchmarking and actually proving quantum advantage is also trickier than it sounds. It's really hard to rigorously demonstrate that a quantum approach genuinely offers a practical advantage for a meaningful AI problem when classical algorithms and hardware are also constantly improving, getting better all the time. You're essentially trying to hit a moving target, so the comparisons need to be done very carefully. And finally, maybe related to that, researchers are still actively working to identify the true quantum sweet spots for AI. It's becoming clear that not every AI problem is going to benefit from quantum computation. Some might even be slower on a quantum computer. So, precisely figuring out which specific types of tasks, which data structures, which kinds of optimization or simulation problems are uniquely suited to quantum speedups or entirely new quantum approaches. That's a key research direction. We need to know where to focus the effort and resources most effectively.
Right. We've covered a huge amount of ground here. We've taken a really deep dive into this fascinating, complex fusion of quantum computing and AI, pulling out those key insights from the sources you provided us with. It seems abundantly clear this isn't just, the next incremental step in technology. It feels more like a frontier that could fundamentally reshape how we compute and how we solve some of the world's hardest problems.
I think that's a fair summary of the overall picture, looking at the sources as of mid-2025. It's definitely a field buzzing with immense intellectual energy, driving intense global research and attracting serious investment, with Canada certainly playing a notable role. The key takeaway, I think, isn't that quantum computers are poised to replace classical AI anytime soon. That's not really the point. Rather, they represent a potential, powerful, specialized tool. Think of it as an accelerator, maybe, or a source of entirely new algorithmic inspiration, specifically for tackling those currently intractable problems, particularly in areas like optimization, simulation for science, and perhaps even discovering fundamentally new forms of machine learning down the road. And the focus for the near future, certainly for the next few years as the hardware continues to mature, as the sources strongly suggest, will likely remain heavily on developing and refining these hybrid quantum classical approaches, using the strengths of both worlds. Classical computers for the general purpose tasks they excel at, and quantum processors for those specific, carefully chosen subproblems where they might offer that unique quantum advantage. It's a really dynamic, iterative path forward.
It truly is remarkable just watching these two revolutionary fields start to converge and influence each other like this.
Absolutely. And maybe that leaves us with a final provocative thought for you, the listener, to mull over. Given this accelerating pace of development we're seeing in both AI algorithms and quantum hardware, how might our very fundamental understanding of what computation even means, how might that need to evolve to fully grasp the potential when these two incredibly powerful forces are completely unleashed, working together? It's definitely something to ponder as this extraordinary scientific and technological journey continues.